Today we're going to talk about how to write a polynomial function given the zeros. So if we are given the zeros of the polynomial, we are actually given the answers. So x equals -4, -3, and 5. Those are the values for x that when you plug them into the equation, you get 0 back out. So we're going to take those and we're going to write them backwards as factors. So in order to get -4 as an answer, the factor needed to be x plus 4. To get -3 as an answer, the factor would have been x plus 3. And to get 5 as an answer, the factor would have been x minus 5. Now, looking at this, depending on what you're being asked to do, you would go ahead and either leave it like this if it's a factored form, or you would go ahead and put this in standard form. So that's what we're going to do right now. You are going to pick two of your different binomials, and you're going to go ahead and distribute it. So you're going to get x squared plus 7x plus 12. Then you're going to go ahead and distribute one more time in order to get this in standard form. And lastly, after you distribute, you are going to go ahead and combine like terms. Since we're writing a function, we do want to go ahead and use function notation here. And this says of least degree integral coefficients, which means we could actually have a function where something would be squared here, where a root would be repeated. But because we want the least degree, we don't want that ambiguity of what is the multiplicity. So we're going to leave all of these as a multiplicity of 1 and then distribute everything. And you notice all of our coefficients here are whole numbers. They're not fractions. They're also not square roots or irrational or complex numbers. So they're all integer coefficients. Lastly, once you do this, if it's in standard form, you can always check your answer by graphing it. So notice how I have f of x equals x cubed plus 2x squared minus 23x minus 60. And notice your x-intercepts here are -4, -3, and 5. And if you compare that to what we started with, -4, -3, and 5 match up. So graphing helps you check your answer. So this next one, we have an I. We have this imaginary number. So for things like this, I'm going to scroll back up one more time and look at the complex conjugates theorem. So if you have an imaginary number as a 0, then the conjugate is also going to be a 0. So if we think back to conjugates, if we had 2 minus 4i, the conjugate would be 2 plus 4i. If our number was 5i, our conjugate would be -5i. So complex numbers all have conjugates, and you're going to take and you're going to change the symbol in between the real part and the imaginary part. When you get a solution that's an imaginary number, we always get them in pairs because imaginary numbers come from square rooting negative numbers, and when you square root negative numbers, you have to write the plus and the minus. So if the minus was a solution, that means the plus was also. So if we look at number 2, if 2i was a solution, what that means is -2i was also a solution. So when we are doing this one, let's go ahead, let's tackle this -1 first. This is going to become x plus 1, but this is happening twice. So we're going to write x plus 1 squared because it's a repeated root and it got repeated twice. For this imaginary part, so in order to get x equals 2i as an answer, or x equals -2i as an answer, I want you to think about how those answers come about. These answers come about from square rooting a negative. So we know if we had to square root a negative, we would get that imaginary part, and then the number we had to square root to get the 2 would be 4. So if we had the equation x squared equals -4, and we square root both sides, we would get +2i and -2i as our roots. And so we can use that to then go to our factored form. So we can move this 4 to the other side, and our factored form would be x squared plus 4. Okay? So a side note over here, let's say we had 5i as an answer. In order to get 5i as an answer, you would have had to square root a negative 25. So our factor would have been x squared plus 25. That's the idea when you have a complex number where your a value is 0 for those. Okay, so that was just kind of another example over there. Now we have to take this and we have to go ahead and distribute this. So I'm going to start by distributing the x plus 1 squared, which is not x squared plus 1. It is x squared plus 2x plus 1. Then what we're going to do is we're going to go ahead and distribute from there. And combining like terms gives us x to the fourth plus 2x cubed plus 5x squared plus 8x plus 4. Now when you graph this, you should see a bounce point at -1, but the other two are imaginary, so you won't see those on your graph if you're checking your answer. So that's the idea. Now some things kind of pop up here. Now we have some more kind of complex numbers here, so we're going to leave this in factored form. So I'm just going to go ahead and jump to the answer for the first part. 0 comes about when x by itself is your factor. -5 would give us a factor of x plus 5. But the part we need to be careful about is the 3 plus I. So you have two options. Again, if 3 plus I is an answer, that means 3 minus I is an answer. So you could say this would be my factors, but that is really messy to distribute. So you could treat it just like you treated the 5 and change the sign in between those. But again, I don't really want to distribute a trinomial times a trinomial here. So what we could do is we could use our shortcut. So instead of doing that, we're going to use the sum and the product shortcut for writing factors. So to find the sum here of specifically the 3 plus I and the 3 minus I, that would give us 6, which, as a reminder, that sum is going to be in front of your x term, but it's going to be the opposite of this. So this, again, was the negative sum. And at the end went the product, if you took your two roots and you went ahead and multiplied them. So let's go ahead and do 3 plus I times 3 minus I. When you distribute that, your middle two terms are going to end up canceling each other out. So you get 9 minus I squared, which is -1. So that becomes 9 plus 1, or 10. So our factor that gives us x, or 3 minus I and 3 plus I as our answers are x squared minus 6x plus 10. And you'll notice this one again lets us leave it in factored form, so we could leave it like that. Now you can always do your quadratic formula with this quadratic factor over there to see if it ended up working out correctly. Let's go ahead and try another one here. So we're going to write this in factored form. I'm just going to go ahead and jump down here because I can write the first two without too much of an issue. I have x plus 3 and x minus 1. So if 4 minus 2i is an answer, so is 4 plus 2i. So for these ones here, I'm going to do my sum. And my product. So when I do my sum, I get 8. When I do my product, my middle terms cancel out. I get 16, and then it's going to end up being plus 4, or 20, which means my factor is going to be x squared minus 8x plus 20. Okay, And so for our very last one here, we have our graph given to us. So with this one, we don't know if there are any imaginary zeros or not. We only see 2 turning points, which means we know the degree has to be at least 3, and that is verified with the 3 zeros there. So we're only going to use the real zeros that we see because we cannot allude to any imaginary zeros unless we're given more information. So for this one here, our zeros happen when x is -5, x is +2, and x is 7. So our factors are going to be x plus 5, x minus 2, and x minus 7. So thank you very much for listening. I hope this helped, and let me know if you have any questions. Thanks.